Hello, calculus students. So for this video, I want to do a little pre-calculus review. Now, pre-calculus itself is quite a large course. There's a lot of material there, so we certainly can't cover everything. But I want to go over some of the things that I think are most important. And what I hope that you do as you're watching this video is, in addition to getting a refresher, I hope that you're looking at, do I know this stuff? Does this stuff seem familiar? And if a lot of it seems really unfamiliar or you just feel lost here, this is a good sign that you really need to go back and brush up on your pre-calculus material, perhaps even enroll in a pre-calculus course instead of a calculus course so that you position yourself well for success here. Let's start with rules of exponents. There are several rules that you have to go by when you're dealing with exponents. First of all, what does an exponent mean when you say a to the n? Well, that just means a times a times a n times. And here we're assuming that n itself is a positive integer, so n is 1, 2, 3, 4, so on, numbers like that. And then whenever you see a negative exponent, something like a to the negative 3, the negative just means to reciprocate. So a to the negative n is 1 over a to the n. And by convention, we just accept that a to the 0 is equal to 1. When you multiply two powers of a, so a to the m times a to the n, you just add those exponents. That's a familiar rule, I hope. And when you divide a to the m by a to the n, you can think of that two ways. So a to the m over a to the n is a to the m minus n. Or if you want to have the expression in the denominator, you can express it as a to the 1 over a to the n minus m. So often when you're dealing with fractions that involve exponentials, you want to move the expression from one side of the fraction to the other for whatever convenient purpose you might have in mind. Now, when you take a power of a, say a to the m, and then you raise that to another power n, you just multiply those exponents. And because multiplication is commutative, m times n is n times m, you can write that way, which then in turn you could write this way. So the main point here is that you multiply the exponents whenever you're taking a power of a and then you're raising that to another power. In these last three rules here, the n and the m, those exponents could have been negative integers too, okay? And then you also run into fractional exponents sometimes. So the key thing to understand when you want to understand so-called rational exponents is a to the 1 over n means the same thing as the nth root of a. And of course we understand that when n is even, we need that the number that's inside the radical has to be non-negative. So a has to be bigger than or equal to 0 when n is even. But if n is odd, a can be whatever number in the world. And then we can also do like a to the m over n, and we can interpret that to mean a to the 1 over n all raised to the m, or we can interpret it to be a to the m all raised to the 1 over n. And so when you convert those two expressions into radicals, you get what you have at the bottom there. So a to the 1 over n and then all raised to the nth power is the nth root of a all to the nth power, like that. But if you first raise a to the m and then take the whole thing to the 1 over nth power, that just means the nth root of a to the m. This time the exponent m is inside the radical with the a. So this gives you some flexibility in manipulating these expressions with radicals that have exponents inside. You can move those exponents out or move them in as needed. Let's look at a few examples. So this is just a reminder of what the rules are. Let's do some examples where we do these rules. So what I would like you to do for each one of these examples, I want you to pause the video and try it for yourself and see if you get the same answer that I get. See if you're remembering the rules correctly. So what I'm going to do in these next 1, 2, 3 examples, 4 examples, is 5 examples here. I'm just going to simplify those expressions. If there are any negative exponents, I want to convert them to positive exponents, and just simplify it as much as you can. That's the goal here. Let's start with the first one. Press pause and try it. Now here's how I would do it. I'd multiply the 3 times the 4 to get 12. I would multiply the x to the 4th times the x to the negative 7th. And remember, the rule is when you're multiplying two exponentials that have the same base, you just add the exponents. So x to the 4th times x to the negative 7 would be x to the negative 3rd, 4 minus 7. And the same thing with the y terms there. I'll multiply the y terms, add the exponents, and get y squared. And then I would like, oftentimes we want to see all positive exponents. So I'll convert this so that it's all positive exponents, and then I would have 12 y squared all divided by x cubed, because that x to the negative 3rd power means the same thing as 1 over x cubed. So this I would consider a simplified answer here. I don't want you to come away from this thinking, though, that negative exponents are somehow bad or less desirable. Sometimes they're a little bit more intuitive to work with, and so for that reason alone, sometimes people want to convert things to positive exponents, but it's totally okay and sometimes even desirable to leave things in terms of negative exponents. But for the purposes of these exercises, I'll convert everything to positive exponents as needed. Okay, let's try this next example. So again, we're going to simplify it the same way we simplified the first one. So this would be a good time to press pause and try this one for yourself, and then after you've done it, start the video again and let's see if we get the same thing. Okay, so first thing I'm going to do here is divide 2 into the 8 to get 4. And for those powers of x there, I see the larger exponent of 4 is in the numerator. So what I could do is write this as x to the 4 minus negative 2. Because when you have one power of x over another power of x, you subtract the exponents like that, right? And then I think since the larger exponent of y is already in the denominator, then I'm going to do y to the 15 minus 9 in the denominator. And that'll give me a grand total of 4x to the 6th over y to the 6th. I could even, if I wanted to, write this in this form. I could write it as 4 times x over y, all to the 6th like that if I wanted to. But either one of these would be sort of fine simplifications of the original. Okay, so let's have a look at this next one. So if you haven't pressed pause already, press pause, try it for yourself, and let's see what we get. Okay, so when I do it, I'm going to distribute this exponent here and write it as 3 to the negative 3rd x to the negative 4 times 3. And then I'm going to have y to the negative 5 times negative 3. So after doing the multiplications here, I'm going to have 1 over 27 is 3 to the negative 3rd. And then I'm going to have that negative x to the 12th. So I'll go ahead and put that in the denominator as x to the positive 12th. And then I'm going to have y to the positive 15th in the numerator. So I'll write it like that. Okay, how about this next one? We have negative 8 to the 5/3. Well, I can interpret this as the cube root of negative 8, and then that's all raised to the 5th power. And I know that the cube root of negative 8 is negative 2, so this is negative 2 to the 5th power. And let's see, negative 2 to the 5th. I think that's 32 negative, so negative 32. And then at the bottom here is an example that involves a rational exponent, but with variables. So give this one a whirl, press pause, and then see if you get what I'm getting now. Okay, so I'm going to have 3 to the 3/2, x to the 4 times 3/2, and y to the negative 8 times 3/2. So what is 3 to the 3/2? I mean, well, 3 to the 3/2 is 3 to the 3/2, but if you wanted to see it in sort of a radical form, you could write that as the square root of 3 cubed, which is 27. So let me just put 27 inside the square root. And then x to the 4 times 3/2, well, you can cancel the 4 and the 2 there. So you get 2 times 3 is 6, that'd be x to the 6th. And y to the negative 8 times 3/2, so it'd be negative 4 times 3, it'd be y to the negative 12th power. So I think for my final answer, I'll write this as x to the 6th times the square root of 27 all over y to the 12th, like that. If we really wanted to simplify a bit more, we could say that 27 there is 9 times 3, so I could take the square root of the 9 and write this as 3x to the 6th times the square root of 3 over y to the 12th. So maybe that would be your simplest form of your answer right there. By the way, as we were going along here, I noticed that we were using some rules that I didn't necessarily write down on the previous page. I was just writing down the rules that came to my mind. But notice that on this third example, I was taking advantage of a property that says something like this. A times b to a power n, let's say, is a to the n times b to the n. And here, in the problem just before that, I actually took advantage of a similar property that says something like a over b to a power of n is the same as a to the n over b to the n. So those are a few more properties that you might want to keep in mind when it comes to exponents. So, for each of the topics that I'm going to talk about in this video, it's not a bad idea to make note of what general topics are giving you trouble. So if you're finding that exponents are giving you trouble, you should Google tutorial on exponents. And there's lots of things on the internet that can give you lots more examples and good downloadable materials. Think places like Khan Academy. Those are great resources, especially for review. Okay, next topic. Let's talk about rationalizing the numerator or denominator whenever you have fractions that involve radicals. This is a kind of clever way to manipulate expressions involving radicals. The goal is, like if I have a radical in the denominator, I want to manipulate the expression so that the radical is no longer in the denominator. I want to sort of move it up to the numerator. So this process is called rationalizing the denominator. And the way you do this is you multiply by a well-chosen 1. In this particular case, I would take that fraction 1 over the square root of x minus 4 and multiply it by the square root of x plus 4 over the square root of x plus 4. This is called multiplying by a conjugate. What I'm really multiplying in red there is 1. I'm multiplying by 1, and we know that it's okay to multiply by 1. It doesn't change the value of the expression. So when you perform that multiplication, in the numerator, you're going to get square root of x plus 4. And in the denominator, well, maybe you go down here and do a little scratch work. How do you multiply square root of x minus 4 times square root of x plus 4? Well, you do that so-called FOIL method, right? Multiply the first, the outer, the inner, and the last, and then combine like terms. So square root of x times square root of x there is just x. And then square root of x times 4 would give me 4 square root of x. And then multiplying the inner terms, I'd get negative 4 square root of x. And multiplying the last terms there, I get minus 16. Notice that the positive 4 square root of x and the minus 4 square root of x cancel out. That's kind of the point. We multiplied by that conjugate because that has the effect of making the middle terms cancel and getting rid of the radical. So what we're left with in the denominator is x minus 16. So this expression is equivalent to the original expression, but the difference is that the radical term in it is now in the numerator instead of the denominator. Really important process for calculating the kind of limits and a little later derivatives that we want to do in this class. Here's another example involving radicals. This time the radicals are in the numerator, and I want to rationalize the numerator, which means to rearrange the things so that the radicals are in the denominator instead of the numerator. So I'm going to do the same trick. I'm going to multiply by the conjugate. So I'm going to multiply by square root of x plus h plus the square root of x this time, because you just do it, whatever the sign is in the middle, you change it, right? But you got to multiply by the same thing top and bottom so that you're really multiplying by 1. And when you multiply it out in the numerator, you're going to get x plus h, multiplying the first terms. The middle terms cancel just like before in the previous example, and then you get minus the product of the outer terms, or the last terms, and then you get minus x there. And then in the denominator, I'm just going to leave that as h multiplied times the square root of x plus h plus the square root of x. And then I can simplify this a little bit further, because in the numerator you see that there's an x and a negative x that cancel, and so you just have h in the numerator, and then in the denominator you have h times the square root of x plus h plus the square root of x. And now I see that I can actually cancel those h's off too, there and there. So this ended up reducing down to 1 over the square root of x plus h plus the square root of x. So there we go. So multiplying by conjugates to rationalize a numerator or a denominator is a process we'll use quite a bit in this class. So you want to know that. Okay, let's talk about factoring. There are a lot of situations where you have to be able to do things like factor the expression so that you can cancel some things and simplify. And so let's go through some common factoring out things. So one way that you factor is you look for common factors and you pull them out, right? So when I look at this first expression here, this 3x to the fourth plus 6x cubed minus 24x, what does this have in common? Well, I can see just by scanning over the terms that I could pull out a factor of 3 and I could pull out a factor of x from all those terms. That's common to all those terms. And then when I pull that out, the first term would have x cubed remaining, the second term would have 2x squared remaining, and the last term would have just 8 remaining. Okay, how about this next, the second part? This 3t squared times the quantity 4 minus t minus 7 times t minus 4. Well, what's catching my attention on this example is this 4 minus t and t minus 4. The difference between 4 minus t and t minus 4 is only a negative. So I'm recognizing that I could write this as 3t squared times 4 minus t, and then plus, if I factor a negative out of that second term, I can reverse the order like that. So now I see the same exact term here, the 4 minus t and the 4 minus t, so I could pull it out, and I'd have 4 minus t multiplied, and then what's left in the first term when you pull out 4 minus t is just the 3t squared, and what's left in the second term is just the 7. That's a way of factoring that expression. In this third part, you can employ a method called factoring by grouping. Like I noticed that if I group the first two terms and then group the second two terms and then factor what I can that's common out of those terms, I see that I could factor 2a to the third out of the first two terms, and that would leave me with, let's see, a plus 4. And on those second two terms, I noticed that I could pull out 4a as a common factor of those two terms, and that would leave me with, I'm pulling out a negative too, so I'd be left with a positive a and then plus 4. And then further, I'm seeing I now have a common factor of a plus 4, so I can factor a little bit more by factoring out the a plus 4, and then that would leave me with a plus 4 times 2a cubed minus 4a. And I see that I can even do one more thing. On that second, the set of parentheses, the 2a cubed minus 4a, well, I could factor 2a out of that if I wanted to. So let me pull that 2a all the way out to the front here. So I have 2a plus a plus 4. And then when I factor 2a out of 2a cubed minus 4, I would be left with a squared minus 2. And probably that would be a sufficiently reduced answer, although you could actually factor it a little bit more. You could factor it as 2a times a plus 4 times a minus the square root of 2 times a plus the square root of 2, if you really wanted to. So anyway, factoring, very important, because the idea is a little bit later, whenever you have a fraction, sometimes you can factor the numerator, and you can also separately factor the denominator, and then you'll see that you've got common things that can cancel off and give you a simpler expression. So super important to be able to factor. You may remember factoring quadratics, or trinomials they call it sometimes. So for example, this x squared minus 7x plus 12. Remember the trick on factoring quadratics is, and they don't always factor nicely, but if they're going to, you figure out terms that multiply to give you the first term, x squared. Well, x squared clearly has to be x times x, right? That's the only way you're really going to factor that. And then you think about how you factor the constant term 12. And whatever the factors of 12 are that you find, they have to add up to what the middle coefficient is somehow. So if I want two numbers that multiply the 12, but then add up to negative 7. So I'm thinking negative 3 and negative 4 here, because negative 3 times negative 4 is positive 12. That's the constant term. And then when you add up the middle terms, you're going to get a negative 3x and a negative 3x and a negative 4x gives you negative 7x. So hopefully you remember this process. It can be a little trickier in some situations because you got to check a lot more possibilities, like 6x squared plus 13x minus 28. Well, I might start with like 6x and x to get the x squared part of it. And then I would think about ways, what are some ways that you can factor 28? Well, you can get 28 as 28 times 1. That's not really going to work here to get 13. And then 14 and 2. Let's see, 14 and 2. No, that's not going to work. 7 times 4. 7 in the middle, 4 over here. No. Yeah, I don't see a way to make that work. So if I can't get it to work with 6x and x, I could try 2x and 3x. Let's see if we can get something going here. 28 and 1 are not going to work. 14 and 2. No. 7 and 4, let's see. Maybe. What if I had 7 here and 4 here, and a positive and a negative there? So when I multiply this times this, I'm going to get negative 8x. And when I multiply here and here, I'm going to get 21x. 21x minus 8x is in fact 13x. So yeah, that's the factorization you need there. So sometimes they can be a little bit harder, but you may have to check a few different possibilities. But hopefully you vaguely remember this procedure. There are other special things that you look for. Differences of squares come up, and you want to be able to factor them. So like 4x squared minus 25 here, that's really 2x squared minus 5 squared. And I know that differences of squares will factor like this. It'll be the 2x, you do minus 5, and 2x plus 5. So what we're taking advantage of here is the property that for any two numbers, a squared minus b squared always factors as a minus b times a plus b. So you just need to figure out what your a and your b are in a given situation. So like the second example there where you have 10t to the fourth minus 1, I could think of that as 10t squared, quantity squared, minus 1 squared. So in the difference of squares formula in red toward the top, on the right there, the a is equal to 10t squared and the b is equal to 1. So I could write this as 10t squared minus 1 times 10t squared plus 1. Sums and differences of cubes also come up, often enough that you should probably know how to factor them. There are a couple of formulas. A cubed plus b cubed, the sum of cubes, always factors as a plus b multiplied times a squared minus ab plus b squared. And the difference of cubes, so a cubed minus b cubed, always factors as a minus b times a squared plus ab plus b squared. And so in the example that I have there of 8x cubed plus 27, I see that that's a sum of cubes because that's 2x quantity cubed plus 3 cubed. So using the sum of cubes formula, this factors as 2x plus 3 multiplied times 2x squared, so that'd be 4x squared. It's 2x the quantity squared, minus the a times the b, so that'd be minus 2x times 3, so minus 6x, and then plus the b squared. The b is 3 here, this would be plus 9. And you can multiply that back out and see that it actually does give you the original expression that we started with. I find that students often don't remember sum and difference of cubes, but it does come up, so I think you should probably, sum and difference of cubes formulas probably should be committed to memory. And then there's your old friend, the quadratic formula. Perhaps you learned some sort of song or dance to memorize it when you were a kid, but here it is. This formula tells you what the roots of a quadratic equation are. So if you start with the equation ax squared plus bx plus c, so you got a quadratic equation where the coefficients of the quadratic thing are a, b, and c. And this formula only works when a is not equal to 0, because if a is equal to 0, you'd get 0 in the denominator of that expression. And besides that, if a was equal to 0, you wouldn't really have a quadratic, you'd just have a linear. So anyway, that's the quadratic formula that you know and love. Now, it's kind of an ugly expression that you don't want to have to use. It involves radicals, and easy to make a mistake with it, with signs and just making arithmetic mistakes. So you usually go out of your way to not use it. It's sort of a weapon of last resort. So if I wanted to solve that first equation, 2x squared plus 8 equals 0, well, I quickly realized I don't need the quadratic equation to solve this, because I could isolate the x squared term pretty quickly by subtracting 8 from both sides and dividing both sides by 4. And so I'd have x squared equals negative 4. And then I would look at that equation and go, hold on a second. No real number squared is equal to negative 4. And so in this class, we're only interested in real solutions. So we would just say no real solutions here, because the square of a number can't be negative. Now, if you wanted to do the complex solutions, you could take that x squared equals negative 4 and take the square root of both sides and say x is equal to plus and minus the square root of negative 4, which is plus and minus 2 times the imaginary unit I. So I didn't need the quadratic formula to figure that out, right? Now, could you have used the quadratic formula? Sure. You would just put a is equal to 2 and c is equal to 8 and b is equal to 0 into the quadratic formula, and you'd get the same answer. On the second one, there's a little typo there, it should be x squared. But on that second one, I'm looking at that and I recognize that quadratic factors. So I could write that one as, looks like I could factor it as x minus 3 times x minus 2. So I've got x minus 3 times x minus 2 equals 0. And then we have this nice property of real numbers that anytime two real numbers are multiplied together to give you 0, one or the other must be equal to 0. So we can say here that x minus 3 equals 0, or you could have x minus 2 is equal to 0. And then those two linear equations can be solved lickety-split, and you get x equals 3 and x equals 2 are your solutions. On the third one, you might try to factor it, but in this case it won't factor, or it won't factor nicely. So you need to use the quadratic formula here. So on this one, using the quadratic formula, you're going to get x equals, so you do negative b, so that would be positive 4, plus or minus the square root of b squared, so that's 16, minus 4 times the a term, which is 3, times the c term, which is negative 5, all divided by 2 times the a term, so that's 2 times 3 is 6. So you get 4 plus and minus the square root of 16, looks like plus 60 over 6, and we can simplify this a bit. So 4 plus and minus square root of 76 over 6. Well, 76 is, let's see, 4 goes into that. Let's see, 4 into 76. Oh, 36, 19 times over 6. So it looks like I could pull a 2 out of that radical and I'd get 4 plus and minus 2 square root of 19 over 6. And then I could factor a 2 out of the numerator. So for the grand finale, I would get 2 plus minus square root of 19 all over 3 for my solutions. Notice that's two solutions, right? 2 plus the square root of 19 over 3, and then separately 2 minus the square root of 19 over 3. So occasionally you might have to whip out the quadratic formula, but like I said, it's kind of a weapon of last resort. You could just always use it if you just want to have one method, but usually if you can factor things or isolate x squared easily, then you do it that way instead. Okay, next topic. We need to talk about how do you simplify rational expressions. Well, rational expressions, those are just fractions, right? So the key thing that you got to remember is it's factors that cancel. Individual terms do not. So what do you mean by factors? Well, we just talked about factoring things, right? Factors are whenever you take an expression and you write it as products of things multiplied together. Like in this first example that I have here, the numerator is not expressed as products of things. It's expressed as a sum of things, sum and difference. So if you want to cancel things from the numerator and the denominator, they have to be things that are factors in the numerator can cancel with factors in the denominator. So how could we start factoring here in this example? Well, I see that I could factor out an x squared in the numerator, and that would leave me with x squared plus 3x minus 4. And I see that I could factor an x out in the denominator too, and then I'd have x squared plus 4x minus 5. And just for emphasis, I'm going to write that x squared is x times x. And then I noticed that that x squared plus 3x minus 4 can factor as x, let's see, plus 4 times x minus 1. And then down in the denominator, I've got x times, looks like I could factor that as x plus 5 times x minus 1. Yeah. Okay, so now the numerator and the denominator are both expressed as products of factors, and I can cancel off any factors that are the same in the numerator and the denominator. So I can cancel off one of those x's, and I can cancel off those x minus 1s, and what I'm left with is x times x plus 4 over x plus 5. So the original expression is equal to that, but when you look at them, they're not exactly the same thing algebraically. So they're not exactly equal. They're only, like for example, I could plug x equals 1 into the final expression, but I could not plug 1 into the original expression because it would yield 0 in the denominator. So if I can plug 1 into one thing, but I can't plug 1 into the other, those two things aren't identically the same, right? But they are the same so long as you can't have x can't be 0 or 1 in order for this equation to be true. I also can't plug 0 into the original expression, right, because it yields 0 in the denominator, but I can plug 0 into the final expression. So as long as x is not equal to 0 or 1, those things are equal. How did I know to exclude the possibility that x equals 0 or x equals 1? Well, I look at the terms that got canceled, and that guides that choice, okay? So the thing in yellow, though, here is really key. So a common mistake that I see students make is when they do something like, oh, they've got something like x squared plus x over x squared, and they do something like this. You can't cancel those x squareds like that. I haven't factored out x squared in the top, so it's not something I can cancel with x squared in the bottom. Okay. Another thing that you run into when you're dealing with fractional expressions is you want to combine a sum or a difference of fractions into a single fraction. And so in order to do that, you need to do the process of getting a common denominator. So if I wanted to get the common denominator of x plus 2 multiplied times x minus 4, I would need to take the second fraction there and multiply it times x plus 2 over x plus 2. And I would need to take the first fraction and multiply it by x minus 4 over x minus 4. And what I'm really doing is multiplying by 1, so I'm not changing the value of the original expression. And so when you do that, you get x minus 4 over x minus 4 times x plus 2 minus 3 times x plus 2 over x minus 4 times x plus 2. And now these two fractions have exactly the same denominator, and when two fractions have the same denominator, you can combine them into one fraction simply by either adding or subtracting the numerators as indicated. In this case, we got to subtract, and so we'd get x minus 4 minus 3 times x plus 2 all over x minus 4 times x plus 2. And then let's see what we can simplify out in the numerator there. When I distribute that negative 3, I'm going to have a negative 3x. Combine that with the 1 times x, I'll have a negative 2x. And then I'll have negative 4 and negative 6 is negative 10. All over x minus 4 times x plus 2. I guess I could go ahead and factor a negative 2 out in the numerator and write that as x plus 5, all divided by x minus 4 times x plus 2. So yeah, I don't see anything else nothing else can cancel or anything here, so there you go. The next example here is an example of what's called a compound fraction. And whenever you have compound fractions, there are a few tricks that you can do to sort of simplify them. So a compound fraction is whenever you have a sum or difference of fractions divided by a sum of fractions or a difference of fractions. And so in this case, we have a difference of fractions in the denominator, so they call this a compound fraction. One thing you can do is you can multiply the numerator and the denominator by the same thing so that it clears out the fractions on one side of the fraction. Or another thing you can do is do the process of getting a common denominator in the denominator and numerator separately. In this case, the numerator doesn't involve fractions, so I wouldn't have to get a common denominator up there, but in the denominator, I could get a common denominator. So I think I'm going to go that route. And so I would write this as x squared y plus xy squared plus y cubed. Okay, if I do the process of getting a common denominator of x times y in the denominator, then I would get x cubed minus y cubed over xy. So all I did was get the common denominator in the denominator of the compound fraction. And then, when you divide by a fraction, it's the same as multiplying by its reciprocal. So I could write this as x squared y plus xy squared plus, I'm noticing that I could factor a y out in the numerator, so I'm going to go ahead and factor that y out. And I'll have y times x squared plus xy plus y squared. And then multiplied times the reciprocal of that fraction in the denominator, so over xy over x cubed minus y cubed. And now I'm seeing a difference of cubes that we know there's a formula for factoring a difference of cubes. So I'm going to apply that and see what happens. I think something good's going to happen because x cubed minus y cubed factors as x minus y times x squared plus xy plus y squared. And I'm seeing something great happening here. This cancels with this. And so what am I left with here? I'm left with xy squared divided by x minus y for the final answer. So it's really important in calculus that you're able to do your algebraic manipulations. And if you're working a problem and you're not seeing how to do the algebra immediately, you need to be able to find resources to help you do that kind of problem. So being able to categorize the type of problem that you're looking at and then find, what are the relevant rules and techniques for simplifying them is important. And if that fails, you can always come ask your professor. As we move into the class of calculus, sort of toward the middle of it, we start needing to solve equations. So there's a process called finding critical points of functions that involves solving equations. So there's a lot of different kinds of equations that you need to know how to solve. You need to know how to solve linear equations. You need to know how to solve quadratic equations, which we talked about previously. But there are so many different kinds of equations. There's logarithm equations, exponential equations, equations involving radicals. We don't really have the time to do them, but I just want you to know that the general skill of being able to solve equations is important. So one type of equation that we could talk about solving, just as a refresher, is solving rational equations. This comes up quite a bit. So remember, rational expressions are just fractions. So we want to solve equations that involve fractions. So a standard strategy here is to take the least common multiple of the denominators of the fractions involved in the equation and multiply both sides of the equation by that LCM. So in this particular case, notice in this first example here, notice that denominator on the right-hand side of the equation factors as x times x minus 2. And then I see a factor of x minus 2, and I see a factor of x. So it looks like if I multiplied both sides of this equation by x times x minus 2, it would clear the fractions. So that's the idea of multiplying by LCM. It clears all the fractions out. So multiply this whole thing times x minus 2. And when you do that, what do you get? So you multiply, you distribute over to multiplying through the whole equation by it, right? So when you multiply the 3x plus 1 over x minus 2 times x minus 2, the x minus 2's cancel, and you end up with x times 3x plus 1, plus when you multiply 4 over x times x minus 2, the x's cancel, and you get 4 times x minus 2 left. And on the right-hand side, the x times the x minus 2, the whole thing cancels, so you're just left with negative 8 after multiplying through. And now all the fractions are gone. Awesome. And so I think I will distribute the x and distribute the 4 here and get 3x squared plus x plus 4x minus 8. And then I still have negative 8. Well, that's nice. I see that those negative 8s, I can add 8 to both sides of the equation. So I end up with canceling those negative 8s off. And I have 3x squared plus 5x equals 0 left over. And that I can pull an x out and have 3x plus 5. So I get x times quantity 3x plus 5 equals 0. And from there, if I set both of those individual factors equal to 0, I would get x equals 0 or x equals, so if you set 3x plus 5 equal to 0 and solve for x. Then move the 5 over and divide by 3, you get x equals negative 5/3. Now, you have to, whenever you do this trick of multiplying both sides by, the LCM, you can introduce extraneous solutions. In this particular case, you can't have x equals 0 because x equals 0 makes terms undefined in the original expression. So I have to exclude x equals 0 as a solution, right? Because you can't plug x equals 0 in right there. You also can't plug it into that fraction either. You get 0 in the denominator. Can't divide by 0. But you can plug x equals negative 5/3. So it's always a good idea when you're doing this method that you plug your solutions into the original expression and see if it actually works. And you can check that if you plug in x equals negative 5/3, it is a solution. So that's a solution there. All right. So anyway, the idea is multiply by something to clear all the fractions out. Makes it easier. Okay, next let's talk about functions. One of the first things you need to think about when you're thinking about a function is what's the domain of the function. So those are just the numbers for which that function makes sense. And the way that you typically define the domain of a function is to remove from the real numbers any numbers that would result in division by 0 or that would result in negative numbers inside of a radical with an even index. Like, so you don't want to take square root of a negative number or fourth root of a negative number, that sort of thing. Because the kind of functions that we're interested in dealing with this class only involve real numbers. So we don't want to get any imaginary or complex numbers. And also, we want to rule out any negative numbers happening inside of a logarithm. So let's look at this first function. F of x equals 1 over the square root of 9 minus x squared. You look at what's going on in the denominator, and you see that you got 9 minus x squared inside that radical. So you need 9 minus x squared to be greater than or equal to 0, so you don't get a negative number in the radical. But you also have a fraction here, and you don't want to get 0 in the denominator. So you also need 9 minus x squared greater than 0, well, not equal to 0, so that you don't divide by 0. So putting that together, you need 9 minus x squared greater than 0. And of course, that factors as 9 minus x, I'm sorry, not 9 minus x, 3 minus x times 3 plus x. And I can see that plugging in either negative 3 or positive 3 is going to make that equal to 0. So one quick thing you can do is, once you know what makes it equal to 0, you can put those numbers on a number line, so negative 3 and positive 3, and then you can just check the sign of that expression. In this case, I'm looking at 3 minus x times 3 plus x, and I want to know where is it positive. Well, if I plug a number to the left of negative 3, like say negative 4 as a test point, I'll get, negative 4, 3 minus negative 4 would be positive 7 times 3 minus 4 is negative 1. So it'll be negative over here. If I plug in something like 0 in the middle, I'd get 3 times 3 would be positive in here. And if I plug in, say, positive 4, I get 3 minus 4, that's negative, times 3 plus 4 is 7. So it would be a negative times a positive, so you get negative over here. So what I can read from this is that 9 minus x squared is greater than 0 on the interval from negative 3 to positive 3, endpoints not included. So the domain of this function, the numbers that we're allowed to plug into the function, it's the interval from negative 3 to 3. So that looks like an ordered pair, but we're talking about the interval, right? So we're talking about this interval negative 3 to positive 3. So you gotta, if you have a function, you have to know what numbers you're allowed to plug into it so that before you can do any calculus with it. So this is important, and it's sort of an often overlooked thing. On the next example here, I've got g of x is the natural log of 4 minus x squared. Well, logarithms may be a little bit fuzzy in your memory. That's natural. But one thing that you should know about natural logs is that you can't plug negative numbers or 0 into a natural log. Natural log of 0 is undefined. Natural log of a negative number is undefined. So just like in the previous example, I can think about what I need here. I need 4 minus x squared to be positive. And when you think about 4 minus x squared, it's just like the previous example. One way to think about this, 4 minus x squared is a parabola with the vertex at 4, and it goes through the x-axis at negative 2 and positive 2. So where is that positive? Well, you can see pretty clearly that it's positive between negative 2 and positive 2. So here the domain of g is going to be the interval from negative 2 to positive 2. because that's where it's in. That's the values of x where the input of that function will be positive. And the endpoints can't be included because it's equal to 0 there, and natural log of 0 is undefined. If someone hands you the graph of a function, you can read off what its domain is just by looking at what are the x values that correspond to points on the graph. So in this particular example here, the x values that correspond to points on this graph are those points from 0 to 8. And the range, you may remember, those are the output values of the function. And you can see the output values of the function by just reading off what are the y values that correspond to points on that graph. And I see that the y values of this graph range from 1 up to about 5, so it'd be one interval 1 to 5, and the endpoints are not included because you got those open dots on the graph there. So sometimes you'll see problems where you need to deduce this information about domain and range just from the given graph. I think those are easier than having to think about the algebra and inequalities like we had on the previous example, but still something you need to know. Sometimes you need to be able to plug things into a function and deal with it. Now, most of the time people are very comfortable with plugging just regular old numbers into a function, but sometimes we need to plug algebraic expressions into a function too. That's really important in calculus. So for example, we got this function f of x equals 5 minus x cubed. So if I say, what's f of 3? Well, that just means put 3 in for x, right? So you do 5 minus 3 cubed. So it'd be 5 minus 27 equals negative 22. Similarly, f of negative 2, you would do 5 minus negative 2 cubed. So that would be 5 minus negative 8. Notice I'm being careful with my signs here. So I'm going to get positive 13. Now, if someone just gives you another variable a, what's f of a? Well, you do the game exactly the same way. Well, f of a just means put a in place of x. So I'd get 5 minus a cubed. And if I wanted to do f of a little bit more complicated algebraic expression like x plus h, again, that just means put x plus h in place of x in the original expression. So I'd get 5 minus x plus h quantity cubed. And then this last expression here, this f of x plus h minus f of x over h, this is a special kind of fraction called a difference quotient that you're going to be doing a lot of in this class. To evaluate that, I would go, well, what's f of x plus h? So it helps to break these fractions down into their individual pieces. So I got an f of x plus h there, and I've got just f of x. We just did f of x plus h in the previous part. So that would be 5 minus x plus h cubed. Then you do minus, and then f of x. Well, that's just 5 minus x cubed. Notice I'm using parentheses there because that minus will have to get distributed all over h. Now I may want to simplify this. So I think if I were going to try to simplify it, I would multiply out that x plus h cubed. And when you do that, you get minus, it'll be x cubed plus 2x squared h plus 2xh squared plus h cubed minus, then you have a minus 5 and then a plus x cubed, all divided by h. And hopefully you notice that the 5 and the negative 5 cancel, and then there's going to be a negative x cubed and a positive x cubed that cancel. And so you're going to be left with negative 2x squared h minus 2xh squared plus h cubed all over h. And then you may notice that an h can be factored out of the numerator, leaving you negative 2x squared minus 2xh plus h squared all over h. And now I've got a factor of h in the numerator and factor of h in the denominator, and I can cancel them, just leaving 1 in the denominator. So the final answer would be negative 2x squared minus 2xh plus h squared. Another process you need to be able to do involving functions is composing them. So that just means essentially that you're going to plug one function inside of another. So here are two functions. X squared plus 5 is f of x, and g of x is sine of square root of x. And so the composition f composed with g of x, that's the first one. So this little circle here means composition between the f and the g there, the little circle. So that doesn't read fog. That's not an O. It's a smaller circle operation between f and g. So that just means to do f of g of x, like that. And so that would be f of g of x is sine the square root of x. And how do you do f of sine of square root of x? Well, that just means take sine of square root of x there and put it in place of x in the formula for f. So if I put sine of square root of x in place of x in the formula for f, I'd get 2 times, and then x squared is, you get your sine of square root of x, whole thing squared, plus 5, like that. And you can compose in the reverse order, but you don't necessarily get the same answer. So this isn't like multiplication. This would be g of f of x for the second part. So that's g of 2x squared plus 5. And then that means put 2x squared plus 5 in place of x in the formula for g. So then you'd get sine of the square root of 2x squared plus 5. And notice that we didn't get the same answer both times, right? When I reverse the order of composition, get two completely different answers. A little later, when we're doing a rule called the chain rule for calculating derivatives of functions, which is one of the main points of this class, is learning to compute derivatives and learning how to use them. The chain rule involves dealing with compositions of functions. So compositions of functions it's an important thing to understand in calculus class. Okay, logarithms. These are the ones that always scare everybody because everybody sort of forgets how to do them. Logarithms are just the inverse process of doing exponentiation. So anytime if you say y is equal to natural log of x, it means exactly the same thing as saying e to the y equals x. So notice y is the exponent. So I said y is natural log of x. Natural log of x is the exponent that you raise e to get back x. And you can have logarithms with other bases too. So if we say y equals log base b of x, that means exactly the same thing as b to the y equals x. So what you want to think when you see a logarithm, let's say log base b of x, it's asking you, it's the exponent to which you raise b to get x. So log base b of x is the exponent to which b must be raised to obtain x. Let's do a few examples here. Log base 2 of 8 down here, these list of examples. This is asking you, to what power do you raise 2 to get 8? Well, 2 to the third equals 8. So the answer is 3. Log base 10 of 100 is asking you, to what power do you raise 10 to get 100? Well, hopefully you see that the answer would be 2. So the first one was true, this is since 2 to the third equals 8, right? And those two equations, 2 to the third equals 8, means the same thing as log base 2 of 8 equals 3. And this one is true since 10 squared equals 100. So the answer that you get when you do a logarithm is the exponent. To what power do you raise 5 to get 1 over 25? Well, the answer is negative 2, because 5 to the negative 2 is, in fact, that's 1 over 5 squared, right? So 1 over 25. Again, the answer was negative 2 because that's the exponent to which you raise 5 to get the thing that was inside the logarithm. And then natural log of e squared, that's just saying, when you see ln, natural log, that the base is e. So it's saying, to what power do you raise e to get e squared? Well, the power to which you raise e to get e squared is 2. So this is true since e to the 2 equals e to the 2. So this one seems kind of silly, but you notice in each one of these things, whatever number was inside the logarithm, that was what we were getting on the right-hand side of this equation. So I was saying, to what power do I raise 10 to get 100? To what power do I raise 5 to get 1 over 25? To what power do I raise e squared to get e squared? Or to what power do I raise e to get e squared? So anyway, you need to be able to work with logarithms like on this level for sure, because sometimes it's nice to be able to give you examples where you don't have to use a calculator, okay? It's like if someone asks you what log base 2 of 14 is, well, I can't think of off the top of my head, like in some easy way, like 2 to what power equals 14? Well, 14 is not a perfect power of 2, right? So in those sort of situations, you may need to get a calculator out if you need a few decimal places of accuracy. But you also need to be able to do the ones where you don't really need a calculator. Okay, and so there's a lot of properties of logarithms that you kind of need to be aware of because we're going to be using them to simplify expressions. In fact, we have a process a little later called logarithmic differentiation, which takes advantage of all these logarithm properties to simplify a function prior to differentiating it. So you've got sort of a sum property or a product property. I'm not sure whether, yeah, it's called the product property. So when you do log of x times y, you can break that up as a sum of log of x plus log of y. Whenever you do log of x divided by y, you can break that up as log of x minus log of y. The third property there is a really nice one. Whenever you take log of x and then the x is raised to a power, basically you can bring the power down in front of the logarithm. So logarithms destroy exponents is a beautiful thing about them. So if you got a problem that involves exponents and the exponent's giving you trouble, sometimes you can use this property to sort of get the exponent out of the way. That fourth property there, b to the log base b of x is x. This is just sort of an expression of the fact that exponential functions and logarithms are inverses of one another. So raising b to a power and doing log base b are opposites, and so they cancel each other and just give you the x. Same thing's going on in the fifth property there. Log base b of b to the x is just x. The last property is called the change of base formula. So this tells you how you can change logs with the base of b into logs with base of e, in other words, the natural log. In calculus class, natural log's the very best log. So we often want to convert things into natural logs, and so this is the way that we convert. Okay, so here's a few examples of how we could take advantage of these logarithm properties. So in this first example, what I want to do is take that expression that's a logarithm and I want to expand it out into a sum and difference of multiple logarithms. So what you can do is realize that when you see square root of something, that's the same thing as raising to the 1/2 power. So I can write this as natural log of 3x cubed y to the 4th all to the 1/2 power. And then I can use the property that says you can bring an exponent down in front of the logarithm. So I can write that as 1/2 natural log of 3x cubed y to the 4th. And then we had a property that says that whenever things are multiplied inside the logarithm, you can break that up as a sum. So I can write this as 1/2 times natural log of 3 plus natural log of x cubed plus natural log of y to the 4th. And now I can take advantage of those exponent properties again that says that you can bring the exponent down in front of the logarithm. So this would be 1/2 natural log of 3 plus 3 natural log of x plus 4 natural log of y. So there you go. So there's sort of a much, in some ways, simpler form of the original expression, because the original expression involved radicals and exponents, whereas the final expression that we have here doesn't have any exponents to deal with. That's what logarithms are really good for. They demolish exponents, and exponents can be problematic sometimes for us. We can also run this sort of process in reverse. Like this next example, I've got something separated out into sum and difference of logarithms with there are no exponents. So, I could start putting things in terms of their exponents like this here. So here I just pulled the 2 up on the first term as an exponent. I pulled the 1/3 up on the y term, which means cube root, so I wrote it as cube root. And then now it's a sum and difference of logarithms, so I can write that as products and quotients. The negative terms go in the denominator and the positive terms stay in the numerator, so you get something like this. Natural log of x squared times 1 plus x divided by cube root of y. The cube root of y went in the denominator because it had the logarithm associated that was negative, right? So there you go. You can rewrite that way. And sometimes, like I said, in calculus, we really like natural logs. When possible, we'll often convert things into natural logs. And also, like if you're going to have to punch things into a calculator or a computer, they usually don't have like a log base 2 button. Usually they have either natural log button or log base 10 button, or often has both of those, but usually don't have the weird bases. So it's kind of nice to convert these to different logarithms. One thing I might do on this one is go ahead and, so that x has a 1/2 power on it because it's square root. So I can pull that 1/2 out and write this as log base 2 of just x. And then the change of base formula says that log base 2 of x would be natural log of x divided by natural log of 2. So in other words, I could write this is natural log of x just over 2 natural log of 2. All right. So there's some things to know about natural logs. Last little topic that we'll talk about here is a little bit of trigonometry. Again, trigonometry can be a whole course, right? A whole quarter or semester long course could be just on trigonometry. It's very important stuff. And I'm just going to hit some of the high points, some of the I feel like are the really most important things to know. But really, I mean, you need to have had a course on this stuff. It's not like you can just take a 2-day seminar on it and be done. So if you've never had really a full course on trigonometry or a pre-calculus course where trigonometry is a major component of it, if you took a pre-calculus course where trigonometry was 1 week of it, that's not enough. Self-evaluate a little bit and think about whether you really have had much trig. If you haven't, a lot of this stuff's going to seem mysterious. All right, let's start with radians and degrees. So the fundamental way to convert from one unit system to the other is 180 degrees is pi radians. So if you think about, a full circle, when you divide a circle into degrees, the full circle is 360 degrees. And this is a vestige of calendars, right? I mean, back in the old days, they approximated the yearly calendar as 360 days. And so, 360 as a measure of angles, associating measuring angles with the number 360 is just an artifact of the fact that the Earth goes around the sun in approximately 360 days. It turns out, though, to not be a very good mathematically, it's not a very good system mathematically. It's more complicated. The more natural way to divide up the circle is to think about how many times the radius of the circle will wrap around the circle. And it turns out that if you take the radius of the circle and you wrap it around the circle, it goes exactly 2 pi times. Measuring the circle in terms of its radius is a more intrinsic way of doing things that's more universal. So converting 135 degrees into radians, you could do that just by multiplying by the appropriate conversion factor. So 135 degrees is the same as 135 degrees multiplied times pi over 180 degrees. Usually we don't write RAD as like a unit. We usually just drop units when we're talking about radians. So when I do pi over 180 though, I'm really multiplying by 1 because pi radians and 180 degrees are equal to one another. So multiplying by 1 here. So when you simplify this fraction of 135 over 180, it comes out to 3/4. So this is 3 pi over 4 radians. But like I said, we usually don't write radians. But if someone wrote radians, you know what they're talking about. Okay, 7 pi radians. How many degrees is that? I can go back the other way too. So to do that, I just do 7 pi over 6 and then multiply by 180 degrees over pi radians. So now, I'm basically canceling off the radian units and being left with degrees. And so this is going to, when you cancel the pi's and you multiply, simplify the fraction, this will work out to be exactly 210 degrees. And then you have trigonometric functions, sine, cosine, tangent, cotangent, secant, and cosecant. Whenever the angle that you're putting into these functions is an acute angle, that means between 0 and 90 degrees, you can think of it in terms of a right triangle here. And I've labeled, with respect to the angle x, an opposite side I'm calling O for opposite, and A for adjacent to x, and then H here is for hypotenuse of the right triangle. So the way we define the trigonometric functions of that angle x, sine of x is the opposite over the hypotenuse, so O over H. Cosine is the adjacent over the hypotenuse, so A over H. Tangent is the opposite over the adjacent, O over A. Cotangent is the reciprocal of tangent, it's the adjacent over the opposite. Secant is the reciprocal of cosine, so it's H over A. And cosecant is the reciprocal of sine, so H over O. So for example, let's see if I can keep all this in the frame together. In this example at the very bottom here, I've got a triangle, and the opposite side of theta is x, and the adjacent side is 4. So I don't know what the hypotenuse is right now. Let me just put h there. But I could say, the Pythagorean theorem says that h squared equals x squared plus 4 squared, and I could solve for h and get h equals the square root of x squared plus 4. And I don't do plus or minus here because I'm talking about the length of a triangle's side, so it can't be a negative amount. So now I know h is equal to square root of x squared plus 4. And so now I could write down, what is sine of theta? Well, sine of theta is, again, the opposite over the hypotenuse, right? So that would be x over the square root of x squared plus 4. And cosine of theta, being the adjacent over h, would be 4 over square root of x squared plus 4. And tangent of theta, being the opposite over the adjacent, would be x over 4. And then we could get the other three trig functions just by reciprocating these. So cosecant theta would be square root of x squared plus 4 over x. Secant, being the reciprocal of cosine, would be square root of x squared plus 4 over 4. And cotangent of theta would be 4 over x. Being able to deal with trigonometric functions when you're thinking about a right triangle is especially important whenever you're doing some real-world problems. A little later in the class, we'll be doing a kind of problem called related rates problems, which are sort of story problems that where you relate how fast things are changing. And oftentimes, a trigonometric relationship evolves around a triangle in the picture. And also, we do a kind of problem called optimization problems, and oftentimes, because of the sort of geometric situation that's going on, there will be a triangle, and it involves trig functions. So trig functions are very important for doing measurement. You can expand the idea of a trigonometric function to non-acute angles by thinking about the so-called unit circle. So the setup here is you take a circle of radius 1, so it's centered at the origin, and then you form an angle from the positive x-axis to just some ray emanating from the origin that I've got indicated in blue there. So that angle theta is the angle that we're measuring. So that angle could be more than 90 degrees like I've drawn it. And then that ray is going to intersect that circle at some point, x comma y. And we define sine of the angle to be the y coordinate there. So sine of theta would just be y. Cosine is x. Tangent is y over x. Cotangent of theta is x over y. Secant of theta is 1 over x, and cosecant of theta is 1 over y. So it turns out that when you're dealing with an acute angle, you get exactly the same answers in this setup as you do with, the right triangle picture that I drew a little bit ago. And then there's the infamous or famous, depending on your point of view, the unit circle diagram. So it's useful so that we don't always have to get a calculator out, and we can do some examples that just emphasizes what the concept is without getting so hung up on like plugging things into calculators and getting decimal approximations. It's useful to memorize this picture where you've got some common angles that are like multiples of 30 degrees and multiples of 45 degrees. What those angles are measured in radians. So 30 degrees is pi over 6, 45 degrees is pi over 4. So knowing those angles in radians around the circle from 0 to 360, and then also knowing what the coordinates are on the unit circle at those points, this is really something that you need to commit to memory, so that from knowing this picture, I could ask you things like, hey, what's cosine of 7 pi over 6? So in my mind, I kind of pull up this picture and I go, okay, 7 pi over 6 is this angle over here. And if I'm thinking about cosine, I'm thinking about the x coordinate. So that'd be negative square root of 3 over 2. Or if I wanted to know what's tangent of 11 pi over 6, then, I find that angle in my mind. Or I just draw a picture. And on this one, you're doing the y over the x, so it'd be negative 1/2 over square root of 3 over 2. And those 2's cancel, and you just get negative 1 over square root of 3. To be quite honest, I don't really have this whole diagram memorized, but I have a way of thinking about it that allows me to extract those coordinates pretty quickly. However you want to think about it, this is something you need to know, because there will be a lot of problems where I'm just going to ask you to do something, and I'll use one of these special angles so that you don't need to be using a calculator, because on all of our quizzes, you're not allowed to use calculators, okay? And this is important, and it's going to be important in Calculus 2, Calculus 3, multivariate calculus. As you go on, all of your teachers are going to expect you to know this. So you might as well, if you haven't learned it already, do it now. Take 30 minutes or whatever it takes to sort of get these values in your mind and quiz yourself over it a little bit and just keep it there. So here's a few of these examples. I want to kind of show you how I think about it. So like I said, I don't really have the unit circle memorized, but let's say I want to do cosine of 3 pi over 4. So mentally, I know that 3 pi over 4 is this angle that's at 45 degrees in the second quadrant. And then I know that those points that are on the 45 degree angles have coordinates like square root of 2 over 2 and square root of 2 over 2. So I just have to decide what the signs are. But if you're in the second quadrant, the y is positive, but the x is negative. So the x coordinate there is negative square root of 2 over 2 at this angle 3 pi over 4. And so then, since I'm doing cosine here, I know the answer is negative square root of 2 over 2. If I was going to do the sine of 5 pi over 3, well, first I have to locate where is 5 pi over 3. Well, I know that 5 pi over 3 is this angle that's sort of down here. It's like essentially 60 degrees downward into the fourth quadrant. So this is 5 pi over 3 here, if I go around that way. And I just know, I can kind of visualize, like at that point, if I think about the x-coordinate's about a half, and the y-coordinate is sort of close to negative 1. So that's your negative square root of 3 over 2 when it's close to negative 1. So I can tell that this is negative square root of 3 over 2. And so on and so forth. You should try to see if you can figure out what tangent of negative pi over 3 is, or secant of 7 pi over 6. You know, in a lot of these examples that you run into in story problems that involve right triangles, there may be some variables involved in the triangle thing, and so x and y here might be some changing quantities, but you know some angle, right? And so like here in this picture, the fact that I know the angle is 60 degrees and I know one of the sides of the triangle, the hypotenuse, is 10, it allows me to actually figure out what x and y are exactly. So for example, I know that from this picture, cosine of 60 degrees is the adjacent side over the hypotenuse, so that's x over 10. So from that, I see that x is equal to 10 times cosine of 60 degrees. But from the unit circle, I know the multiples of 30 degrees, I can get exact values for those. So cosine of 60 degrees, let's see, that's going to be 1/2. So this is 10 times 1/2, which is equal to 5. And similarly, I see that if I do sine of 60 degrees, that's y over 10, the opposite over the hypotenuse. And so y is 10 times sine of 60. And I know that sine of 60 degrees is square root of 3 over 2 from my unit circle knowledge. So this is 10 times square root of 3 over 2. The 10 and the 2 cancel. You get 5 times the square root of 3. See, an exact answer on the money answer. I didn't have to plug that into a calculator and get some decimal thing. I can get it done faster and more precisely just by knowing a few values from the unit circle. It's going to come up sometimes that you have to solve equations that involve trigonometric equations. Usually that involves, what you want to do is isolate the trig function on one side of the equation and get it equal to some number, and then use your knowledge of the unit circle. So on this example here, 2 times cosine of 2x equals 1, I can divide both sides by 2 to isolate the trig function. So I'd have cosine of 2x equals 1/2. And so I just have to ask myself, where on the unit circle is cosine equal to 1/2? And so I think about a picture. Cosine is the x-coordinate, so it's just saying where on the unit circle is the x-coordinate 1/2. So it's at these angles like this, which it's like pi over 3, and then 5 pi over 3. So I got to have 2x equal to, could be pi over 3, or I could have 2x equal to 5 pi over 3, and then dividing by 2, I could get x is 2 pi over 3, or x is 5 pi over 6. Because we're dividing by 2 and we're trying to find the answers in 0 to 4 pi, I probably need to consider, what if I go fool around, like go all the way around once and then come back to pi over 3? Pi over 3 is in the same position as, if you add 2 pi to that, so adding 2 pi to that would be, well, 7 pi over 3. And if I added a full 2 pi onto 5 pi over 3, so add 6 pi over 3, that'd be in the same position as 11 pi over 3. So also, since I'm dividing by 2, I need to consider these cases that 2x could be 7 pi over 3, and 2x could be 11 pi over 3, would give me an answer in the right interval. So I could get x is equal to 7 pi over 6, and I could get x is equal to 11 pi over 6. And all of these answers here are in the interval from 0 to 2 pi. So what this came down to was once I got it to the point where I was thinking about cosine of 2x is equal to 1/2, I was asking about my knowledge of the unit circle. Where is cosine equal to 1/2? And so I knew that, it had to be in the position of pi over 3 and 5 pi over 3. And then I thought to do the 7 pi over 3 and the 11 pi over 3 because I knew I was dividing by 2. So I just had to use my noodle a little bit, but it came down to knowing the unit circle. We also have to work with inverse trigonometric functions. So this is kind of like doing logarithms. You have to think in reverse. Instead of saying what the sine of something is, you got to say at what angle would sine be equal to a given number. So for sine inverse of x here, that just means it's the angle between negative pi over 2 and positive pi over 2 whose sine is x. So if I say, hey, what's sine inverse of negative square root of 3 over 2? It's asking, what is the angle between negative pi over 2 and positive pi over 2 where sine is equal to negative square root of 3 over 2 over 2? And if you go look at that unit circle, you're going to see between negative pi over 2 and positive pi over 2, the place where the y-coordinate is negative square root of 3 over 2 is negative pi over 3. I didn't plug anything into a calculator. I didn't do a computation. I thought about the unit circle. I used my knowledge of the unit circle. Similarly, on the next example here, if I want to do cosine inverse of something, that just means cosine inverse of x is the angle between 0 and pi whose cosine is equal to x. So if someone asks me, what's cosine of negative 1/2? I go, okay, where is the x coordinate equal to negative 1/2 in between 0 and pi on the unit circle? And in between 0 and pi, the x coordinate is going to be negative 1/2 at 2 pi over 3. Again, I didn't do a computation. I wasn't doing sums and square roots and all kinds of crazy stuff. I just thought about the unit circle. And I know the unit circle, and so I got the answer just from memory. And you can do tangent inverses and cotangent inverse, secant inverse, cosecant. All the 6 trig functions have inverses. And this little table that I put here tells you the domain and range of these functions. So if you're going to take the tangent inverse of something, the answer that you're going to get has to be between negative pi over 2 and positive pi over 2. If you're going to do the cotangent inverse of some number, the answer that you get is going to be between 0 and pi. You need to understand the range, domain and range business in order to make sense of even when you're using a calculator, because those calculators are programmed to do exactly the same sort of thing. So for example, what's tangent inverse of 1? Well, from this table, I know that the range of tangent inverse is negative pi over 2 to positive pi over 2, endpoints not included. So I'm looking for the angle between negative pi over 2 and positive pi over 2 where the tangent's equal to 1. Well, tangent's going to be equal to 1 when the x and the y values on the unit circle are equal to one another. And I know that that happens at those 45-degree angles. In fact, tangent inverse of 1 I know is going to end up being pi over 4. If I need a tangent inverse of negative 1, it would end up being negative pi over 4. So I knew pi over 4 was the answer I had to get because that's the angle between negative pi over 2 and positive pi over 2 where tangent is equal to 1. There are other angles where tangent is equal to 1. For example, tangent is equal to 1 at 5 pi over 4. But 5 pi over 4 is not in that range where you're supposed to get that answer. So it's important to understand those ranges in that table. Sometimes this sort of thing happens in calculus class where we need to simplify sort of a composition of a trig function with an inverse trig function. And here we make some assumptions just so that this thing makes some algebraic sense. So the thing to know, anytime you plug a number into an inverse trig function, you're getting an angle. So it's helpful to say, let's let theta equal cosine inverse of 2x. So start thinking of that cosine inverse in this problem as an angle. So this is the same as saying that cosine of theta is equal to 2x. And we also know that the angle has to be between 0 and pi because we're doing cosine inverse. But we were told x was positive also. So I know that the angle theta here has to be acute. So I can draw a little acute triangle here with an angle of theta. And cosine of theta here is 2x, which I can think of as 2x over 1, which on this right triangle it would be the adjacent side over the hypotenuse. So I could go ahead and label on this triangle that the adjacent side to theta there is 2 times x and the hypotenuse is 1. And then if I use the Pythagorean theorem, I can solve for the third side of the triangle and it works out to be 1 minus 4x squared. So from the diagram, we can see that sine of theta, remember sine of theta is the opposite over the hypotenuse. So that's square root of 1 minus 4x squared over 1. But remember what theta is equal to. Theta is cosine inverse of 2x. So what we just found is that sine of cosine inverse of 2x is equal to the square root of 1 minus 4x squared. And that was the simplification that I was looking for. What we find in calculus class is that inverse trigonometric functions are very closely related to expressions involving square roots, just like we have in this example. It's a very important connection between two different classes of functions. So square root functions are very closely connected to inverse trig functions, and especially in the second calculus class, this comes into play in a very big way. Okay, so the last thing I'm going to leave you with is that if you had a trig class before, you know that there's a bunch of identities. So these are equations that are true about trigonometric functions, and it doesn't matter what the input value is. Like, for example, the Pythagorean identities are some big ones, especially that first one. The Pythagorean identity sine squared of theta plus cosine squared of theta equals 1. So you can put any angle in the world you want. Theta could be pi over 6. Theta could be 152 degrees. It doesn't matter. You always get 1 when you do sine squared of theta plus cosine squared of theta. That one you should have committed to memory. Probably the other two committed to memory also, but if you ever forget the other two, you can always rederive them, because starting from, as long as you remember sine squared plus cosine squared equals 1, you could say divide both sides by cosine. If you divided both sides by cosine, you'd get sine squared of theta over cosine squared of theta plus 1 equals 1 over cosine squared of theta. But that's the same as tangent squared of theta plus 1 equals secant squared of theta, which is the second identity right there. So if you ever forget the second one or the third one, you can sort of reobtain it just by dividing by either sine squared or cosine squared. So really, I just remember the first one, and then if I know that there's a relationship between secant squared and tangent squared, so if I ever feel like I need it, I can always recover it. You definitely need to know these quotient identities. These come up a lot. So tangent, you can convert to sine over cosine, and cotangent, you can write it as cosine over sine. Super important. And these reciprocal identities are also super important, so you need to know all these. Like, these just need to be part of your vocabulary. You got to just know them. So commit these to memory, the ones I'm putting in yellow for sure. That's sine of negative theta equals negative sine of theta, and cosine of negative theta equals cosine of theta are useful at times. So I would know those two at least. And you can get the other four from those two pretty quickly by using the reciprocal identities and the quotient identities. Honestly, I don't use those cofunction identities very much. Sometimes they come in handy. But the sum and difference identities for sine and cosine are super important. You should know those by heart. The double angle identities are useful to have in your pocket at all times. So sine of 2 theta and cosine of 2 theta, need to know those. I mean, the other ones on this list, you need to know they exist, and you can look them up if you ever need them. But the ones in yellow come up often enough that you really just kind of need to have them ready to go. So I would commit those to memory. So there's the super fast, high-level review of precalculus. Again, what this was meant to do was to let you know sort of a minimum of things you kind of need to know by heart, and if you're and sort of so you can size yourself up a little bit to see, how ready are you for calculus? Do you need to do some review, or is it a situation where it's beyond reviewing some? You need to learn this stuff. If you're in the situation where you feel like you need to learn this stuff for the first time, then precalculus is the class where you need to be. And if it's just like, oh yeah, I remember that, like most of it you're kind of remembering, but some of it you feel like, well, I know that, but I'm rusty on it. Well, then you'll probably be okay. You just need to knock some of the rust off as you're going. We will have a quiz over precalculus stuff, so I recommend that you start doing some review. On my math lab, I will post some review opportunities. But that's all I have for you today. So we'll stop there, and I'll talk to you again soon. Bye now.